Hello everyone, welcome to GeoBridge. Today I'll be talking about the oldest rocks in Texas, and more importantly, I'll be talking about the oldest rocks you can actually visit in Texas. And of course, since this is GeoBridge, I'm going to be talking about the geologic origins of these rocks, and at the end of all this, you're going to be blown away by how unique Central Texas is from a geological standpoint. So without further ado, let's get into it. So the National Park Service website has this pretty cool map that shows you how old all of the rocks are in the United States. So looking at the legend, the oldest rocks are going to be at the bottom and the youngest rocks are going to be at the top. And as you can see by all the yellow and green areas, the majority of the rocks here are younger rocks. But you do have a few pockets of Precambrian rocks or really old rocks sprinkled all throughout the United States. And if we look at Texas, there's actually not that many Precambrian rocks, but the little rocks that we do have are over 1 billion years old, and they tell a pretty interesting story of Texas's geologic history. So there are 3 places in Texas where the rocks are over 1 billion years old, and they are in the Llano Uplift, the Carrizo Mountain Group near Van Horn, and the Franklin Mountains in El Paso. But unfortunately, this outcrop is so small that it doesn't even show up on this map. And within these areas, the oldest dated rocks are the Hackett Peak Formation, the Valley Spring Domain, and the Kastner Marble. And I personally love the Kastner Marble because it reminds me of those couches from the 80s. But unfortunately, the Kastner Marble is not the oldest rock in Texas. Actually, the Hackett Peak Formation has the oldest rocks in Texas. But sadly, we can't go look at these rocks because the whole mountain that contains these rocks is private property. So that means that the Valley Spring Domain has the oldest accessible rocks in Texas. And now that's going to be the focus of this video because we can actually go check out the rocks and talk about them. And spoiler alert, the Valley Spring Domain has a very interesting rock that is neither igneous, metamorphic, or sedimentary, so we'll dig into that in a bit. So this is a more detailed geologic map than what we saw earlier. So this is a geologic map of Texas, and right in the middle you see this circular package of rocks. This is collectively known as the Llano Uplift, and within the Llano Uplift you'll find the Valley Spring Domain. So this is a closer up view of where the Valley Spring Domain is located, and it's also called the Valley Spring Gneiss, and that's because you'll mostly find gneiss within the Valley Spring Domain. But because you can also find marbles, amphibolites, and schists, they just call it the Valley Spring Domain. But mostly you'll find gneisses where they're outlined here on the map. And gneisses really are nice to look at, especially when they sparkle in the sun. This sparkly aspect is actually how it got its name. So back in the 16th century, Germans were super interested in gneisses, and that's because they were known to host veins of silver and copper ore. And whenever the Germans were developing official mining terms, they used the old German word for spark to name this rock so that other mining prospectors could easily identify a gneiss in the field. And the reason why gneisses tend to glimmer like this is because all the mica grains are aligned in one plane, kind of like a bunch of tiny little mirrors just laying flat in one direction. And this is different from something like this pegmatite, where the micas are in a bunch of different random orientations. So the reason why a gneiss has all of its micas aligned in one direction is because there was this extreme event that squeezed these rocks and forced the grains to grow in the opposite direction of the pressure. And the pressure to actually grow new minerals in this direction was really extreme. The Valley Spring Domain rocks had to be buried to a depth of about 16 miles, and then they had to be baked at 1300 degrees Fahrenheit in order for the minerals to align like this. So it took a tectonic event to metamorphose the rocks into how we see them today. So what exactly happened here in Central Texas, and when did it happen? Well, we'll need to start by going back 1.3 billion years into Texas's geologic past. And this was a time whenever the gneisses of the Valley Spring Domain were first formed. because they weren't always gneisses. They were something else before they were metamorphosed. So back in that time, this area of central Texas was at the edge of the continent. So imagine this is all water, and right here off the coast of Texas, there was an island arc with tons of active volcanoes. And this is similar to what we see with Japan and China today. So Japan is also an island arc, and just how Japan is right off the coast of China, there was an island arc that was just off the coast of central Texas 1.3 billion years ago. So Texas was at the edge, and since this oceanic crust was going underneath the Texas area, a chain of volcanoes along the margin popped up. And this is very similar to what you see in the Pacific Northwest, where there's a chain of volcanoes right at the edge of the continent, and in this case, the Juan de Fuca plate is going underneath the North American plate to produce these volcanoes. So Central Texas looked a lot like the Pacific Northwest. You had the same style of volcanoes. The only real difference is that there were no plants or animals, only single-celled organisms like bacteria. But lots of rocks were forming at the time. There were rhyolite flows, just like what we saw during the Mount St. Helens eruption. And below the volcanoes, there were pools of magma feeding the volcanoes. The remaining magma that didn't get erupted would later cool off and harden into crystalline rocks like granite. There were rivers and streams that had likely reworked all the volcanic deposits and turned them into clay-rich rocks, like shells downstream of the volcanoes. So all the rocks that you see in this scene were the original Valley Spring domain rocks before they got metamorphosed. And for a while, this is what Central Texas looked like, until all of these rocks soon went away because they were about to be metamorphosed. So shortly after Texas looked like the Pacific Northwest, the supercontinent of Rodinia was beginning to assemble. So you may have heard of Pangaea. That's the most recent supercontinent that came together about 300 million years ago. But Rodinia was a supercontinent that happened before Pangaea. So since Pangaea was more recent, the continents still had the same shape, they were just smushed together. But with Rodinia, the continents looked a lot different. You can see in green, Africa was split up into about 3 or 4 individual continents, and one of those continents was actually right next to Texas whenever Rodinia came together. And whenever you have plates coming together like this, mountain ranges will pop up right along the margins of where these plates are coming together. And in the Roadside Geology of Texas 3rd edition, you can actually see where all these mountain ranges popped up. They're shown here in green, and this is where the preserved mountain ranges are, or where we can find rocks that are from those ancient mountain ranges. And if you've ever heard of the Grenville orogeny or the Grenville mountain building event, that's what this is referring to. So all the rocks in green are Grenville-aged rocks, and you can actually find other Grenville-aged rocks in places like the Blue Ridge Mountains. So at this time, the continents were coming together to form Rodinia, and Kalahari, which was its own continent at the time, but now it's part of Africa, well, that was a continent that began approaching Texas shortly after the Valley Spring domain rocks were being formed. And as it was approaching Texas, it shoved the island arc and sutured it to the border of central Texas, and at that boundary where the two collided is where an ancient Himalayan-style mountain range formed. And this is a nice diagram, because it shows how the original rock will get transformed depending on how deep it goes. So you can start with a rock like a slate, and then as you go deeper and deeper, it'll turn into a phyllite, and then a schist, and then eventually a gneiss. So as you can see, the Valley Spring gneisses were easily buried by about 16 miles of overlying rock. And we're only now able to see these once buried rocks because this whole area got uplifted and eroded, and now we're only able to see the roots of these mountain ranges. So 16 vertical miles of mountains got eroded, and actually all around the world, these mountain ranges got eroded, and all that sediment got washed away and dumped into the oceans. And geologists think that all that sediment maybe provided the nutrients needed for complex life to evolve. So it's interesting to think that because of the formation of rodinia, perhaps complex life was able to evolve. So that's just an idea that needs to be tested out some more, but it's cool to think that Texas might have played a role in the evolution of complex life. So now that we know what the Valley Spring domain represents, let's talk about the nicest place you can go to visit this 1.2 to 1.3 billion year old rock. So this map of the Valley Spring domain shows you where it crops out at, and a big chunk of it is on private property, but the Devil's Waterhole at Inks Lake State Park is public, and there just so happens to be great exposures of the gneiss there, and it also is just a good visual showcase of what happens when rocks experience a ton of heat and pressure. So here at Inks Lake, there are a ton of places to see that classic gneissic banding that forms as the rocks experience more and more pressure, which causes the darker minerals to separate out into bands like this. And a crazy thing about Inks Lake is that you can also see what happens when the rocks go too deep and get too hot. So notice how the gneiss is at the end of this whole metamorphic process. Well, when it gets too hot and too deep, these rocks will begin to melt and form these crazy warp patterns. This rock is called a migmatite, and if it melts fully, then it just becomes magma that will later harden into an igneous rock. But at this point, it's sort of an intermediate rock in between a metamorphic rock and an igneous rock. Inks Lake also has a lot of dikes. Unfortunately, that is just the geologic term for a body of igneous rock that cuts across already existing rocks. It's also sometimes spelled with a Y, but I don't know if that really helps the case. But at Inks Lake, you can find dikes that seem to be deformed with the rest of the gneisses, but there are also dikes that don't seem to be deformed at all, and these are interpreted to be part of the Town Mountain suite of granites, which is what Enchanted Rock is a part of. So in other words, it likely originated from the same mantle source as Enchanted Rock. So that's that on the oldest accessible rocks in Texas. It's not every day that you see something that has existed during a time when the Earth didn't even have any plants or animals. And Texas is lucky to have this super nice rock that was able to capture a critical part of its geologic history. And on that note, thanks for watching, and I'll see you in the next video. Bye!